this is just a hard problem that.
This is gonna bother me now.
Are we recording?
Yeah.
Okay, we're recording. We're gonna try to do this quickly so that if something goes wrong, you got something here. All right, here was the warm-up, no peeking. Okay, here's the warm-up. Go ahead and pause me like this, and then write this down and try them on your own. We had a little issue with the SIM card, that's why we're starting late. Okay, here's how the first one should be worked. Good old average value formula, plug stuff in, did the math, yada yada. Okay, an average value of negative 3.5 or negative 1.5. That's not like area where we have more area below.
That's like the average area was
More of the lengths of the points were below the x-axis than were above. They were about 1.5 on average.
It was still,
Lower.
doesn't normally mean, but if the distance between it, how, always has to be positive. So if it's negative, there was definitely more area under the bottom. So if
Correct.
there's more area under, then that means the
It
value
only
of
has
the
2
area.
minutes left.
By the way, you can figure out what the area was just by getting rid of this 1/3.
Yeah.
If we multiply by 3 and get negative 9.5, then that was the aggregate area. This is just the average value of the whole function.
You said it only has 21 minutes left.
All right, we'll do what we can then. They'll get 21 minutes.
Negative, yeah.
That'll get us to at least one example for them.
What's the net area?
Second question is derivative, kicking it old school. All right,
Product chain, double chain.
good. Product, that's a chain, and then this piece right here is actually a couple of chains. That and that are both separate chains. So this one's gonna be chock full of parentheses and garbage like that.
Deliciousness.
Make as much room as I can here. All right, product first.
Keep the first.
Why not?
Get them.
To be sadistic, we can do that. Keep the first, e to the negative x, derivative of the second. Okay, think about this, think about this in terms of outside function, inside function. I see, at its heart, it is something squared. So my outside function is gonna be something squared. Inside that, we have sine. Inside sine, we have 3x, so it's gonna be a chain inside a chain. Derivative of something squared is 2 something to the first. Then we have to chain the first sine with his derivative, which is cosine. Then we take the chain of what was inside of that and get an extra 3.
Bam.
Okay? So this 2 something to the first dx, there's the first chain, and then that was also not an x, so we tack on his chain. This can happen ad nauseum, but I've never really seen them go more than 2 on the AP test. That's about as bad as it gets. Plus, keep the second, sine squared of 3x, times the derivative of the first. Well, the derivative of either anything is either the thing, okay? Either the root of x. And then we're gonna do it.
I think these people are now.
Oh,
These aren't just for me, oh, these are for
There's
kids.
a, yeah. That's how I was looking, I was going, what is that?
I don't know.
Never know what it was.
I didn't get anything.
Amber and Chelsea. Ooh. Amber and
I would say
Chelsea
that
have
they're
an
not
admirer
using
in the
this
back.
black
In the backpack?
Boy's gonna have to use it.
Yeah.
That's how I
Yeah.
was
Cake.
I was like, why do I
Thank you.
have black
Well,
heart?
they
It's
were
about your
supposed-
teeth.
Ladder monkey.
Oh,
Sorry.
sweet.
see ya.
Chain
I like that.
the square root of
She gave
x.
us,
Think about this, hang on, talk after 21 minutes. Think of this as x to the 1/2. Derivative of that is gonna be 1/2 x to the negative 1/2. By the way, you don't need to put plus c because it's an antiderivative, so don't make that mistake, okay? Please don't do that. Free response. Ta-da! I'm done. Okay.
Not.
Choice.
Multiple choice, here's what they would do. I noticed that but you really have 2 halves, this piece and this piece.
Oh,
I
you have
see
a
an
C.
e to the x in common,
Yeah, take that out.
or e to the root of x, right? Check and check. I also see
Sine X.
one sine, so sine of 3x. I got one of them and one of these. The rest of it is nothing in common, so they would have, okay. What's left over is a 6 cosine. Got it? What's left over here is the other sine, and then a 2 root of x on the bottom. Okay, so they would have put plus sine of 3x, and then a 2 root of x on the bottom like that. So that's probably how it would appear on a multiple choice question.
I don't see another way.
There's nothing else you can really do for that. If you're trying to be sadistic and turn it all into sines or cosines, and you could use some kind of trig substitution, but that's stuff that y'all probably forgotten anyway, and they don't really test it on the AP.
Yeah.
Someone was actually asking a question earlier about trig substitution. It's not even on BC, he was watching a video and they did that. It is a valid technique for integration, but not one that we have to learn in AB and not even in BC. So if you're taking college calculus, you'll learn another technique called trig substitution, but we don't. Remember that. All right, ta-da, warm up.
No, it's
Excellent. Now, how do you feel just from yesterday about average value? That should be one of the easiest lessons we've done in a long time. Feel good? Okay. Now on to not quite as easy a concept.
After the storm?
After this-
Is it drizzling?
Oh, it's drizzling, yeah. It's drizzling.
coming in, the clouds are rolling.
All right.
How fast the winds on this one?
The next week for us is gonna be about volume,
Oh, yes.
okay?
Do you want me, can I go do my rotations?
Not yet, okay? Today is not the rotational. Next week is when we do rotational volume, where I spin things and create solids. Think of a potter's wheel, spinning the actual object to create a volume, okay? What we're gonna do today is cross-sectional volume.
Okay.
Technically, the rotational volume is a specialized version of cross-sectional. So we'll knock this one out of the way first, and I'm hoping it'll make the rotational volume make more sense. All right, now it's gonna be a crude sketch day, lots of crude sketching, so bear with me. Let's start with a typical setup. These are very, very wordy. There's like a paragraph of words here. I'm gonna write it once, just so you've seen it, and then I'm going to, for the rest of our examples, just paraphrase what's going on. So here's how they would have worded a problem like we're about to do. The base of a region, they love that, is defined by, let's keep it relatively simple to start with. How about, y equals x squared, y equals 0, and x equals 3. Okay? So the first thing they do is define what the base of our solid, our picture, whatever it's going to be. They give you the zone. Here's the map. All right. Cross sections perpendicular to the x-axis are, what shape would you like? Give me a shape. Don't say octagon.
Square.
Squares, all right? Are squares with one side on the base. This is a classic setup. Define,
That's confusing.
let me draw the picture. Yes, it's confusing, let me draw the picture. Define the actual base and then describe what the slices of that solid are going to look like. Think of a loaf of bread, okay? A loaf of bread, every single slice has the exact same shape. Some of them are bigger, some of them are smaller, but it's the same shape. That's the idea here. When we slice this object, whatever this object looks like, okay, when we slice it, each of the slices is going to be the exact same shape, squares. The difference is that each of those squares is going to be a different size because of how it fits on this region, okay? So I would suggest drawing a picture if they don't give it to you, and 99% of the time with these problems, they have drawn the picture for you. So they've gone ahead and graphed the region and said, Here it is, okay? Now, this is gonna mess with your heads just a little bit, but I'm going to lay our axis down to give it the illusion that it's sitting on the floor, okay? So let's see here, x-axis. Y-axis. Okay? Right there. The illusion I'm trying to create is that we've taken our classic X and Y and I just want to lay it down, lay it on the floor. So imagine the floor as the X and Y axis, and I'm going to draw this area, draw a little zone, and then I'm going to build something inside that zone. Okay?
Okay.
The zone we are going to cut off is y equals x squared, y equals 0, and x equals 3. Here's y equals 0. Here is some arbitrary point I'll just use as x equals 3. Okay, and then y equals x squared would be a parabola. It's going to look a little distorted because I'm laying it down. Okay, so imagine it. It's pretty good actually.
That's really good.
Yeah, so imagine the parabola, I've done enough of these, I should be good at it. Laying down. So, the region that's gonna serve as the foundation is right here, okay? So, it says cross sections perpendicular to the x-axis, meaning this way, perpendicular. We could also do it perpendicular to the y-axis. That means we'll just have to switch everything to y values like we did a couple days ago. For today, I want to stick with x's until we get pretty good at it. When I slice it, here's what the slice is going to look like. Every arbitrary slice is going to be a square with one side of that square on the base. For instance, let's say I were to slice it right here. Okay? Then we would end up with a teeny tiny little square. If I go further down and slice it here, then that particular slice would be a bit bigger because the square has more room to be. Down here at the bottom, it's next to nothing. Over here towards the end, you end up with a much bigger square. Okay, and then every point in between. All right. So in essence, I'm gonna start, they're all coming up out of the graph, okay? So you have teeny tiny nothing square, 0, and then the squares get bigger and bigger and bigger until you hit a square that's basically, which is 3, basically a 9 by 9 square, okay? Because it's, if that's 3, then this length right here would be 9. So start with a little 0 by 0 square, work our way up to a big 9 by 9 square and everything in the middle, and it's gonna make a solid.
This would be interesting how things
Yeah. I remember geometry, yes.
So pretty much, we're just
You know how
making,
beautiful this is.
and so if it's, pretty much we're just elevating that, it's almost, that area, in the case of squares, that area just times the height.
Well, hold that thought.
The
Hold that
lean
thought.
is like playing with my head.
The what is?
The lean.
The lean. All right, let's see if this helps.
I see the squares now, I just have to look at it for a while.
This is the idea.
Oh,
Okay.
that works. That's why.
Okay.
That's why she had those in her classroom.
Who? Ms. Jones?
No, Miss Goldfinch
Oh,
last
yeah,
year.
yeah. She the calculus teacher.
Yep.
Yeah. So here's the region for this particular shape. They've drawn it for you.
Drunk with circle.
And then for this one, the slices were semicircles, and notice that they get small, it's kind of hard to see, but they're small here because the zone is small for them to get trapped in, and it gets bigger because the limit is bigger, okay?
Hey,
So that's basically what we're looking at, and if we have time after the AP, we'll make some new ones of these that we can add to our collection if we want to. Okay, so 2 steps to solving these. Step number 1. Find the area of any given slice, so of a generic slice. Step 2, add them all up. second part's actually the easy one. Okay, first one can get rather difficult.
So it would just be, we could write it as, depends on the side, what a side equals,
All right, what is the area of the shape we are dealing with?
side squares.
All right, so it's a square, and the area of a square, length times width, or side square, because the length and the width are the same thing, so I'll say the area is side squared. I need to find the area of each of these moving squares. Now, what determines how big the square is?
Is X.
No, the area it's from.
No, it's Y.
Right, but we don't know the y value unless we get to the x value first. So here's what I'm gonna do. Go to an x value,
Go to the, and then go to the.
and then from that x value, find out his y value, and then that would tell me what the length is, which would therefore be the same as the height.
What does that say? Add what?
Add them all up,
Okay.
apostrophe em, add them all up. That's how us
Add
Southerners
them.
speak. Yeah,
Yeah.
That's a person.
add 'em, eve them all up, is that right?
Eve 'em all up.
Eve all up,
Ha
add
ha
them all
ha.
up.
Very funny.
For me, nonetheless.
That's a good one.
All right, so for a side, the side is going to be determined by whatever this length right here is. Okay, which is basically, if this is some random x, then the length of it will be whatever the y value is. So, for us, the area in terms of x, one side is the distance from x to that, which is x squared. Squared. One side, side squared to get the area of a square. Pause and let that sink in. Everybody cool?
I'm trying.
And
We're not gonna
Why
start
is
with,
it so-
we're not gonna start with summation, just, and just go and add up and get an average first.
we are gonna do summation. We're gonna add them all up. That's the next step.
So like doing like an average like we were doing with the original here, we're not doing.
Well, kind of. Okay, so that's any one square.
It's X squared.
Now what I have to do is add up an infinite number of squares. That's easy.
Just like this.
It is.
That's all we do is that's us adding it all up is the antiderivative. So now I'm gonna take the volume therefore will be the antiderivative of x to the fourth. What is my window? What is my interval?
0 to 3.
In this particular problem, my x's are going to run from 0 to 3.
Oh.
Ladies and gentlemen, there it is. That, if I just put that on a piece of paper and say do it, you're like, whatever.
This is like, oh.
Yeah.
You have to get, but the getting to that part.
Yeah, this is honestly harder, the pre-algebra is harder than the calculus part of it. So, the volume for us is going to be 1/5 x to the 5th from 0 to 3, which is 1/5 of 243 minus 0, which is
Why'd you,
2,
wait, why'd you write 1/5?
do it, 1/5, sorry, thank you.
I was like 1/3.
Good eye, yeah. 243 over 5, which will not reduce.
And then,
Units cubed, whatever that is, so somewhere in the neighborhood of 50, just shy of 50. Okay?
well,
Now, that is the volume of this weird shape that we're going to create.
it actually looks pretty cool.
That does look pretty cool. You gotta think,
It's
Okay.
really smooth.
one side of the square is here, one side of the square is here, or one corner of the square, one vertex is here.
And it's,
The other two vertices are following the path of these corners. And then the other one is following the path of the outside
kind of
corner.
has like a sonograph.
So it looks like that, or the inside of a speaker box,
Yeah.
something kind of like that. Does that kind of help how the shape comes up like that?
Once you showed me that, then I could picture it better.
That's what I do.
Nice.
And it not only,
It looks like
it's
a-
kind of hard because this side of it is flat, but this side of it kind of curves out because this curves this way. So the shape of the box would actually be tiny and then do this. come out and up that way.
It's like a.
Pretty cool looking, whatever it is.
But we're so lucky the square.
I would say
That's
around,
actually
but
difficult to do.
From the outside, it has flat edges. This side will be flat, this side will be flat, this side would be curved this way, and this side would be curved.
And I'm guessing
That
if
way.
you do a
That's the
rectangle,
same.
the rectangle has to be locked.
If you do a rectangle, you have to define how the rectangle grows. Like, it is a rectangle whose width is always twice its length. So you have to kind of lock in what every single slice is going to be.
Or is it like, yeah, or 2 to 4, like, yeah, but they have that ratio.
You have to, yeah, you have to say, this is how it grows, or else the shape takes on a life of its own, and we can't do a formula for it,
So you
so.
can always just go up and down.
All right, there it is in theory. So I'd make sure you have these two memorized. Just find the area of a generic slice. And then step 2 is the calculus of adding them all up. Technically, we are gonna do summations here, but if we take an infinite summation, we have seen in previous lessons, that just turns into the antiderivative. Okay,
You
Question.
made it.
yes,
So what we're doing is we're just taking the shape,
of a slice.
the shape of the slice, getting the formula for that, and then plugging into the function.
Correct. Plug it into the integral.
Yeah, and
We made it.
bam.
Did it just run?
It's
Oh, all right,
yellow.
so yay,
It's getting
you have one
light.
example, so if the machine cuts off at any point, you have at least one example. Let's try and do another one, hopefully.
It's yellow, but
Yeah.
it's not there yet.
Did that make sense? You got it?
Makes.
Maybe not the calculus, did you understand the theory behind what we just did?
I understood the shape.
Good, good, that's a start.
Oh, we have
Probably got
another person
everything
here.
except
Oh.
for the little anti-rhythm.
We have a guest,
part.
yeah.
She did not get it.
I don't-
Yeah, the antiderivative part will be.
That wouldn't have gotten it, but.
All right, here we go. Let's let the base, I'm not gonna write out the words, we'll just shorthand it. Okay, gosh, what are we gonna do for our base? How about,
That would be really nice. Square root of x.
square root of x?
Sounds pretty.
Let's do that. All right, so y equals square root of x, y equals 0, and x equals
5.
5. Okay. All right, cross sections. Now, for today, assume that when I say cross sections, we're gonna be perpendicular to the x-axis. Semicircles? All right, semicircles,
1/2.
hang on.
So like that one?
Yeah, like that. Semicircles with the diameter on the base.